there's 2 lessons today. The first lesson has 2 parts. First thing I need you to understand is the word dissociation and ionization. Oh, I put 2 I's there. Okay, so in order to do a dissociation equation, you have to kind of ask yourself, first of all, is it ionic, molecular, or an acid? Do you remember Science 10 review? I got you to put an M or an I or an A beside the thing. Remember that? That's what this is. Is it an I? Is it an M? Is it an A? Okay? So no problem. If it's ionic and it is soluble, or maybe it's insoluble. How do you tell if it's soluble or insoluble for an ionic compound? Come on, Science 10 again.
The chart.
The chart. Where do you find that chart?
Periodic table.
Data booklet. Yeah? Everybody okay with that? Okay. So if it is soluble, then when I drop that compound into water, it will dissociate into its ions. Did you get it? So that copper sulfate that you used yesterday, you might have dropped that solid into the water, but when it hit the water, it became Cu2 pluses and SO4 2 minuses in that water. No more copper sulfate. Just copper ions and sulfate ions. Everybody okay with that? However, if I drop something insoluble in, like MgO solid, if I were to drop that in water, it would simply just stay MgO solid. Just stay that way, because it's not soluble. Like a rock is not soluble either, so it just stays as a rock in the water and sinks to the bottom. Only this isn't a rock, it's white powder, and the white powder would stay white powder. Okay? No matter how much you mixed it, it would just still stay. Okay, so if it's ionic, you then think, is it soluble or is it insoluble? And then you can, it'll exist as its ions or it'll exist as the compound. Okay? But what if it's molecular? If it's molecular, how do you tell if it's soluble or not soluble? Well, this is unit 1. Just put your midterm. Polarity. So if it's polar, it's soluble, right? And if it's non-polar, it is insoluble. Okay? Can you give me an example of a polar molecule? How about sugar? Is sugar soluble in water?
Yes.
Okay. So C6H12O6. Does it look like it's probably going to be polar to you with that oxygen sat there? Yeah. And so if I drop solid sugar into water, what does it become? Well, it stays as C6H12O6. So it stays together, but it's now aqueous instead of solid. Okay. And insoluble, nonpolar. So an example of something insoluble nonpolar would be like an oil that's just carbons and hydrogens. Right? So like C50H102. And that would be a solid, or probably liquid actually. And if I put that in water, it would just stay as oil, liquid, floating on top of the water. You already knew that? You already knew oil floats on water, right? You already knew that it's nonpolar because of unit 1. I've written it in a slightly fancier way now, but I haven't said anything different. Yes,
So,
Nick?
how come on ionic soluble it dissociated and not on molecular soluble?
Because I don't have any ions for it dissociates into. It stays as a molecule. Everybody happy so far? Okay. And then what happens when acids are placed in water? Oh, it disappeared on me.
Click edit.
Okay.
And oh.
Yeah.
Never mind. Something.
All right. Well, let's try this. Oh, I know why, because it's not appearing over here, so it doesn't think I'm on board. Oh well, we'll keep going. Okay, so acids. What happens when acids what happens when I put an acid in water, such as HCl? Gas. Yeah, it ionizes. How did you know that? You read it somewhere. Good.
You're awesome.
So, what makes an acid an acid? H pluses. So H plus, there it is, and Cl minus, there it is. Now this is called ionization because I am making ions. Because actually, HCl, there aren't any ions there. It's a shared pair, covalent bonded molecule. Are there any ions in molecules? No. They're just atoms, sharing pairs of electrons. No ions. But when I put it in water, what I say, it's like a divorce. They were bonded together beautifully. Okay, they were very stable in this marriage. And then the divorce happens and chlorine takes it all. 1, 1, no, there's everything brought to the relationship and the extra electron from hydrogen. And that's why it's negatively charged. And poor hydrogen, well, he's left with nothing. Yeah, you should have signed a prenup.
Yeah.
Okay? So hydrogen's left with nothing. He's just a proton. Charged and ready to bond with somebody else, I suppose. Okay. So you've made ions. They weren't ions before. Whereas the dissociation equation, which rubbed off the board, so I'll rewrite it again, but you have it in your notes already. The dissociation equation that we wrote earlier about copper sulfate becoming Cu2 plus and SO4 2 minus, these are just like flatmates. Or like the two of you sat together and I say, you two separate. You two dissociate from each other. I'm dissociating from you. I don't want to speak to you ever again. But I'm still the same person, okay? So copper and sulfate, this is still Cu2 plus, and this is SO4 2 minus, and it's still that way. They have just moved away from each other. Okay? No one took anything from anybody else. They just simply dissociated from each other.
So they had a prenup.
They were already ions. They not only had a prenup, but they also had in their own rights, their own careers, their own houses, their own cars, their own everything. I don't need anything from you. I'm just going to go live in Florida now.
Seems like
They were pretty prepared. Okay? I'm glad you know so much about this,
they were
Nick.
pretty prepared.
Okay.
Just know the song Gold Digger. That's why.
Oh, that's it. You're getting all your information from a song called Gold Digger.
Yeah.
From Kanye.
There's a lot of
Jesus.
hope for your future. Okay. All right. So most of this stuff has been reviewed. Would you agree with that? Yes. Science 10 about whether it's soluble or insoluble, or bonding 1, bonding unit 1. The only difference is that I'm now asking you to write them like this. Okay? Instead. So you're writing them now in these sort of it looks more like an equation. All right? So now here's a harder equation for you. Tell me what's going to happen, and I'm going to click this button again, and it's going to all disappear on me, but that's okay. Oh, except for that little thing there, because it likes that. Okay. Okay, so tell me what happens if I'll just use that. That's Al. If I were to take Al Cl3, aluminum chloride,
That's
and I am going to ask you to put some solid aluminum chloride into a solution, into water. How would that exist? Well, the ions would separate and go over here and they'd be surrounded by water, right? And this one would be surrounded by water as well. So, what ions are surrounded by water? What ions do you see in there? Al. Al doesn't look like an ion yet.
3 minus.
3 plus.
Plus.
Pluses are always on the left. And Cl minus. Is everybody okay with that? Except for here's the thing. In our Lewis dot diagrams that you were drawing, because this is an ionic compound, right? And so in bonding unit 1, I asked you to draw the Lewis dot diagram for these. And you would go on Al square brackets 3 plus. Cl minuses look like this. Square brackets minus, right? And what do you always get one more mark for? Remembering. How many Cl's do I need? I need 3 of these, right? How many Cl's do I get if all these break apart?
1.
I get 1 Al 3 plus and I get
3.
3 Cl minuses. You see that?
Yeah.
So this is what you did in the bonding unit. And now I'm asking you to write it in like a nice straight line. It's the same thing, just looks different though. Okay? Same understanding though, just differently communicated. Everybody okay? So try this one then. If I could rub these out. Try doing aluminum sulfate. Oh, SO4, I mean 3. Write the dissociation equation for aluminum sulfate. Is that what you got?
Yes.
Yeah.
2 Al 3 pluses and 3 SO4 2 minuses.
Yeah.
Yes? Everybody okay? Broden's not. What's up?
No, I got it now.
Okay. So this is kind of like Science 10. If I were to say to you or write in the words aluminum sulfate and make the compound, you would have gone aluminum's a 3 plus, sulfate's a 2 minus, put them together and you get this, right? Because I need 2 aluminums for every 3 SO4s. I need 2 aluminums for every 3 SO4s. So this ties Science 10 as well. What states? I've already got a solid there. I'm dropping a solid into the water. What states go in my ions? Solid. Are they solid?
First, you should probably check your solubility chart.
If you've already done this, there must be soluble. Then what?
Never mind then.
What states?
Aqueous.
Aqueous. Because they are surrounded by water. Okay? So what exactly does this mean then, these numbers? These numbers mean if I have one of these compounds, it'll break up and it'll give me 2 of these ions and 3 of those ions. You okay with that? So if I were to draw this compound, I'd have to draw 2 ALs. You would really draw it like this, but anyway, all kind of hanging out together. These are 3 pluses and 2 minuses, 3 plus, 2 minus, anyway, okay, blah, blah, blah. And then I put it in water, and over on this side, this is the important part, on this side, what would I have to draw? I'd have to draw 2 Al3 pluses and 3 SO4 minuses. SO4, SO4, SO, oh, not 4 of them, 3 of them. Okay? SO4, 3 minus, SO4, 3 minus. 2 minus, 2 minus, 2 minus, 2 minus. Sorry, my mind's somewhere else. Okay, so 2 Al, 3 pluses dropped in there, and 3 SO4, 2 minuses. What if I were to draw 4 Al, 3 pluses? How many SO4 minuses would I have to draw?
6.
6 of them. What if I only drew 1 Al3 plus? How many SO4s? 1.5 of them.
Not possible.
No, not to draw them, but is it possible to have 1.5 of them? No. But actually, in my beaker, am I going to just have 1? How many do I have?
Million, trillion,
Right.
bazillion.
Millions, trillions of them. And in fact, because I don't count them, what do I group them as? A mole. Is it possible to have 1.5 moles of them?
Yes.
Yes.
Oh yeah, like 1.5 dozen eggs. Oh yeah, that's possible. So, if I want to kind of erase all of this stuff. If my relationship, my ratio, is a 1 to 2 to 3, for every one of these I put in solution, I get 2 of these and 3 of these actual things, then for every 1 mole, I would get 2 moles and 3 moles of those. Everybody okay with that?
Yeah.
And if this was all in 1 liter, that would be a mole per liter. This would be 2 moles per liter, and this would be 3 moles per liter. So yesterday, I'm just going to change this to a slightly easier example. Yesterday, you made a solution of copper sulfate. You made 2 solutions of copper sulfate. And the first one had a concentration of 0.05 moles per liter. Is that correct?
Yes.
And that's all we said. We said the concentration of copper sulfate in your volumetric flask is 0.05 moles per liter. But actually, what was in there? Not copper sulfates, but rather copper, 2 pluses, and
Sulfate. 2
sulfates.
minuses.
So, what was the concentration of the copper ions? If it's a 1, makes 1 of these and 1 of these. Then that means 0.05 will make, no. If it's 1 to 1, it's 0.05 to 0.05,
Yeah.
and 0.05 moles per liter of that as well. So if I take my copper sulfate and if I take a dozen of them and I chuck them in, I will get a dozen copper 2 pluses and a dozen sulfates. If I put a mole, I will get a mole of copper ions and a mole of sulfate ions. If I put in 0.05, I will get 0.05 and 0.05. Okay? Everybody okay with that? So let's make it a little harder and do magnesium chloride. When I drop magnesium chloride into solution, what does it become? Mg2 plus and
2Cl.
good, 2 Cl minuses. What are the states?
Aqueous.
Aqueous, aqueous, Sometimes this is aqueous, sometimes it's solid. It depends on whether it tells you a solid was dropped in or whatever. And in this magnesium chloride solution, it was a 3 mole per liter solution of magnesium chloride. What are the ion concentrations?
What's the ratio?
What is the ratio? You tell me.
1 to 2.
1 to 1 to 2. So therefore it's 3 to
3. 6.
6. Yes? What if, the next question asked, what is the chloride it gives you the chloride concentration, pardon me. So it tells you the chloride concentration is 9 moles per liter. What is the original solution concentration?
4.9.
Yes. If it's this ratio still, then it's 2 to 1, so it's 9 to
12.5.
so just divide by 2 because it's 2 to 1. Moles per liter. Does that make sense?
Yeah.
So you've learned how to write a dissociation equation, and you've learned how to calculate the concentration of the ions. So the sheet I've given you takes you through that precisely. So this sheet here. Okay? So you can practice that until the halfway bell, and then I've got the next step for us to learn after that.